pleasure to introduce Steve Wills from University College Cork, who will speak on a favourite topic, the right Hudson Path-Seraphi equation, QSD, the right. Correct.
Is it right versus wrong, or is it right
Both left, right sides. Again, that's a play.
There is deliberate ambiguity in the title here in the interpretation. By this stage of the conference, nobody's literal about anything, I think. As ever, many thanks to the organisers, particularly the local crew, who I know have been working very hard on this. It is always a pleasure for me to come to Bangalore, to come to India in general. It's mainly been Bangalore in recent visits. My history of interaction with the star of the show, KBS, began 21 years ago. We had a brief meeting in France, but then I also turned up at ISI Delhi as a Royal Society INSA fellow, not for as long as Martin, but I was there for long enough, and at a very fortuitous time in that Debashish and Parthor were still PhD students at the time, so I got to witness the birth of a new generation of, might I say, excitable Bengali mathematicians. I got to experience the speed and the high volume of mathematical discussions, mainly in Bengali. And the one Bengali word I learned from all of this is homology. So anyway, yeah, the right Hudson Path-Seraphi QSD. I mean, as a conference, there's actually been not a lot of QSDEs floating about. So I think it's right that at least one talk, and I guess I'm the fool guy for this, should look at these things. So this is the object I want to study, written in two different ways, RHP, right Hudson Path-Seraphi QSDE. I am after a process U. The U are going to be operators. I would love them to be unitary, but I'm not going to worry about that at this stage. I want them to act on this tensor product of two Hilbert spaces. H is going to be a separate Hilbert space. Fock space here, we've seen this a couple of times. Once this morning in Sundar's talk on Thursday it appeared as well. So this is the boson symmetric Fock space over L2 of R+. I'm deliberately keeping things in the language of this morning as one mode of noise. I'll talk about how that can be generalized later on. The right here, if I'm being literal about it, is there is a left and a right Hudson Path HPQSDE. The right here is, does the process, the U, appear on the right or the left of this F? F here, when I've written out in all the different pieces, okay, I've got my process, my U appears in each bit, and I've got other operators, L, G, G, L, K, and M, integrated against various integrator processes. So the A dagger, the N, and the A here are the processes of the HP quantum stochastic calculus. I've got creation, preservation, annihilation. DT is DT. G, K, L, and N here are all operators on this little h, this initial space. Throughout, I'm going to be a bit dodgy and say, okay, G is officially an operator on H, but I'm going to think of it as an operator on H tensor F by tensoring with the identity. My problem is, and the right HP QSD does have a big problem here, is what I want to focus on is what happens when the G, the L, the K, and the M, although it actually won't be the M, are unbounded operators. I deliberately want to deal with unbounded operators. If that's the case, okay, my U's unitary, so this is going to map H tensor F back onto H tensor F, and it will be an onto map, and then it hits this unbounded operator. Does that product make sense? Or rather, which things can I put on the right-hand side of that U that will get mapped into the domain of this tensor product? It's a problem that you have to satisfy, or you have to work out to some extent, in order to actually make sense of that equation. Okay, so that's my problem. It's unremittingly technical. And this is the end of the conference. So, I mean, there will be very little in the way of proof in this talk. I want to use this 40 minutes. When did I actually start on the clock, Martin? Did you check?
A few minutes past.
20 past, was it? Okay. To give kind of a survey of some of the ideas in this, because, I mean, it's not a story that everybody knows brilliantly. I should also point out that this is joint work with my co-author, Franco Fagnola. Joint work that has been sitting in my drawer for longer than it should have done. This is my fault. And we are resurrecting it. I'm actively trying to resurrect it. Okay, so basic assumptions on the G, the K, the L, and the M. Okay, G is going to be the generator of a C0 contraction semigroup. So it's a nice unbounded operator. I'll call that semigroup P. There will be some other dense subspace of my initial space, so some curly D. It's going to be inside the domain of the generator of the semigroup. It will sit inside all four of those components. As a result, f of some vector psi, which takes values, so this is a two-component vector taking values in D and D, that will make sense because the components of psi will sit in the domain of all those four operators. The other thing we need, or we're going to assume, is that this operator inequality, f plus f star delta f. So you saw something quite similar to this construction in Martin's talk this morning. That should be non-negative, but obviously f here is an unbounded operator. So what I really mean is let's hit it with vectors either side, take their inner products, and write it as this form inequality. The delta in here is 0, 0. It just projects onto the second copy. Okay. So throughout my talk, if I talk about f and say it satisfies the standing assumptions, I mean all of this lot. There's good reason to put all this in. In particular, part 2, it just helps because it makes stuff make sense. Part 1, there's a good reason for that, which I'll come back to in a bit. Part 3, if I want a solution that is unitary, this has to happen. This is kind of a necessary condition. In fact, that's a necessary condition just to have a contractive solution, not even a unitary one.
Can you take G as a Schrodinger operator, let's say minus Laplace plus B, to make things concrete? Does it make sense to ask that question?
Yeah, it does.
Right.
Yeah, and you, to an extent, yes, you can, but it depends how you choose the other components there.
You need to be more specific.
Yeah, yeah. Oh, I mean, I will stick in one example at the end, but basically you want, I mean, yeah, if you want to take generators of heat semigroups and stuff like that, it should hopefully work, but there's a bunch of technical conditions you're going to have to go through to check that out. Okay, so as I say, I want to deal with the right one, the one where the process is on the right, the coefficients are on the left. Way back when, sometime in the last century, people studied the left equation, LHP, so left Hudson path Charity quantum stochastic differential equation. Everything in here is the same. I've got my G, my L, my K, my M. I'm still integrating against creation, annihilation, preservation, and time. But I've swapped the order. I've put the V, the process, on the left-hand side. And I'm actually pointing with my left-hand side. That's fortuitous. The coefficients are on the right. Okay. If you assume the F satisfied all that stuff on the previous slide, all of this lot here, if you put these nice conditions in, it is possible to solve the left Hudson path Strathy quantum stochastic differential equation. Your solution will be contractive. So that's in there. I'm starting at the identity as well. You can say more about it. There's a unique solution. There's one and only one solution. Having G as the generator of a semigroup is very useful for proving that part. You can prove more. You can prove that your V is a left cocycle. So it's not a semigroup, but is Sundar still here? I will look around. There was discussion of these objects on Thursday morning when we were talking about the CCR flow. This is a way to construct those objects that Sundar was talking about in his talk. V here satisfies this evolution equation. It's not a semigroup, but it's a semigroup with this twist in it. This is the semigroup, the CCR flow. It's acting on one of the two components pushing stuff forward in time. Okay, so sigma s here is going to take bounded operators on H tensor F. It's going, which splits up as things on the initial space, things up to time s, things beyond time s. And all it does is it takes things in these bits and it just pushes it into the future and leaves me with the identity on that first interval of length s. Okay. So if I start with an f that has all this nice structure, I can go away, I can solve the left Hudson path authority QSDE. I can say more about my solution. When you go and solve that thing, the domain of your V starts off as something like this. The D where my F made sense, or the G, the K, the L make sense. The curly E here are the exponential vectors, which we have seen in a couple of talks this morning. So that's where it will be defined to start with. It will map, or rather the coefficients, this guy here will map things from this smallish space into this slightly bigger space. V being contractive and bounded, I can write it across the whole space so that the whole combination makes sense. This is why the left equation was studied first, because analytically it's easier. There is an argument, neither Franco and I can quite remember it in full detail at the moment, that says the right Hudson, the right HP equation is actually better if you want to interpret from a physics point of view, but please don't ask me the details because I've forgotten at the moment. No, we know the source who we can get this information from. Okay, so as I said, script E here is the space of exponential vectors. These got defined this morning. Sadly, the quantum stochastic community does not use uniform notation for this, so I'm going to be dealing with normalized exponential vectors. So that funny W thing was psi of f in KRP's talk this morning. So that's a unit vector determined by a choice of some f in my space that I'm taking the boson Fock space over. What am I doing on time? Okay, that's fine. What else can I say? Well, I've got my f. If I start with an f and I want to solve the right equation, I'm still a bit mystified at this stage of the talk. I can go off and I can solve the left equation. Does that help in any way? Is there a relationship between solutions of the left equation and solutions of the right equation? There is, and this gadget, which I'm about to explain, is one way to travel from one to the other. Okay, so for any fixed t, R of t is going to act on L2 functions on the half line. It is going to, yeah, I've got that around the right way. On the interval 0s, or 0t rather, it's just going to take the function, whatever it is, and turn it round, reverse it in time. From time t onwards, it does nothing. So it's only acting on 0t in a non-trivial way. After that, it's left alone. Big R is going to stand for the second quantization. So in your normalized exponential vector, I hit it with a little rt. Given any, I'm going to say bounded operator here, but this will work for various unbounded operators as well, I can hit that either side by this big R of t. So little r, it's a nice operator. It's self-adjoint. It's unitary. Its second quantization is as well. So this row of t, which is acting on operators, has some nice properties. What does this have to do with both left and right? Well, yeah. There are two things, two objects in my talk. I've got solutions of QSDEs, and I've got cocycles. On the previous slide, when I was talking about solutions of the left HP equation, I said there was a solution and it was a cocycle. So by solving the equation, the QSDE, I could get a cocycle. There is a converse problem to this. If I have a cocycle, does it necessarily satisfy a QSDE? And there are results in this direction. It's not the subject of today's talk. But this gadget here, I can apply it either to, if x is any bounded adapted process. So adapted just means it's acting non-trivially. Xt will only act non-trivially from 0 to t. There is a filtration on the Fock space. It flips you between left cocycles and right cocycles. Right cocycles I did not define, I don't think. So the left cocycle does this guy, should we do in V? Right cocycle just swaps the order or the component that the CCR flow acts on. Okay. Sigma S being a star homomorphism, it's obvious that if you just take the adjoint of one, you'll turn it into the other. But in fact, this time reversal gadget also turns a left cocycle into a right cocycle. Slightly less obvious, but it is true. The other nice fact, and it comes again from this worrying about when do solutions of QSDEs give you cocycles, when do cocycles give you solutions of QSDEs, and so on. If I assume I'm doing something analytically nice and take the F to be bounded, V being the solution of the left HP equation is equivalent to this time reverse thing being the solution of the right one. When F is bounded, solving one equation or the other is reasonably straightforward. You can give a proof that works for both of them, both equations at the same time. One thing that can happen, and I should warn you, if I take any bounded operator F here, I can always solve the equation, but the U or the V may be unbounded. So my generator, the F, the coefficient in this might be bounded, but the solution might be unbounded. I'm at the stage in this talk trying to deal with an unbounded coefficient and then obtain a bounded solution. Okay. So this row switches me from solutions of one to solutions of the other, at least if F is bounded, and it always will switch cocycles from one side to the other, whether they come from QSDEs or not. So one thing you might hope is, okay, if I scrub out the bounded there and say, let's this be unbounded, I could try and solve the QSDE with the F on, get this right way, with the F on the right, the process V on the left. I could then look at rho and say, is that the solution of the right one when my F is unbounded? It works when F is bounded, but does it work when F is unbounded? Well, that could work, possibly, but I would still have to know something about the range of this U when I apply it to certain nice vectors. So that's what we've still got to work our way towards. Okay. So I've got the left HP equation on one hand. The other thing that you get from this, and this guy is ubiquitous again in the literature, are quantum dynamical semigroups. So again, I have Franco to thank for, well, partly for introducing me to the subject, but also for introducing the subject to all of you on Thursday. My setup compared to his then, he was dealing with bounded generators. I am going to be dealing with unbounded generators. So I've still got two operators. G, generator of a C0 contraction semigroup again. L is some operator defined on the domain of G going back into H. And we have this form generator. So I've got the G's, the K, and the L's in here. X here is any bounded operator, and U and V are vectors from the domain of G. Actually, yeah, sorry, before I get into that quickly. This bit here, this solves it for the left and the right. If you are used to semigroup theory, no, it doesn't go any further. Okay, so this is the usual thing I've been saying. P is a semigroup with a generator G. It's a standard result in semigroup theory that you can put the generator, when you differentiate it, either side of the semigroup, and it leaves the domain invariant. This is true for all psi in the domain of G. So for semigroups, this time reversal thing you don't see. If you solve the differential equation that your semigroup satisfies, you can put the G either side. It commutes with the semigroup. It's not true for solutions of QSDEs. I've done some work which says which Fs you can put either side and get both left and right cocycles. Okay, so back to the story of the minimal QDS, halfway through. Okay. Starting from a semigroup generator and some other operator L, such that we have this form inequality here, you can go off and find a quantum dynamical semigroup. So that's to say operators or maps acting on operators on H. It's a semigroup, so it starts at the identity, it evolves as a semigroup. Each of those TTs is completely positive, so the non-commutative step up from classical positivity of Markov semigroups. Sub-Markov here says the identity is mapped to something less than or equal to the identity, or equivalently it's contractive. I want suitable continuity, and I want it to actually solve the integrated form, essentially, of my semigroup differential equation there. So every time I pick a G and an L, I can go off, and this guy has been shown to exist. It satisfies a minimality condition if T dash is any other semigroup satisfying all of that. The minimality says the one I've created up here is less than or equal to any other one for any positive x. And there are examples where, starting from a G and an L, you can get more than one solution to this problem. If the G and the L are bounded, no. If they're unbounded, subtle things come in, and you can get more than one solution. Okay, where have we seen the G and the L before? Well, they were part of my coefficient. My F, when I wrote it as a matrix, was G, K, L, M. It's this first column in here, which in the QSD is the time coefficient and the creation coefficient. So if I write down something that's supposed to be the coefficient of my QSDE, I assume all the conditions I had before. If I go off and I solve the left Hudson Path-Strathy differential equation, I'm going to let U be the time-reversed guy of that. Well, necessarily, those conditions I put down on F means G and L satisfy the conditions that give me a minimal quantum dynamical semigroup. That semigroup's always there. How is it related to these solutions of my QSDE? Well, the QDS, the quantum dynamical semigroup, is take your solution V of the left HP equation, conjugate x tensor the identity on Fock by your cocycle, and then do this E, which is the vacuum conditional expectation. So it's averaging out the stuff that you get from the noise from F to give you an operator back on this initial space. So that just means stick in the vacuum vector either side here. It's the same as putting in U, the time-reversed object. That's not hard to see because this rho T, it's a multiplicative map. Rho T of A, B is rho T of A, rho T of B. When he sees things that act just on the initial space, it doesn't change them because it's only acting on the Fock space bit, and it leaves the expectation invariant because if you reverse 0 in time, it's 0. Okay, if a function's flat and constant and you switch it around, it's the same. So I can put in V or U, it doesn't matter. So, where am I up to so far? Start off with an F, assume it satisfies all the standard conditions I want it to do. I can find a solution of the left HP equation. I can produce the minimal QDS for that G and L. That QDS, that quantum dynamical semigroup, has other uses when it comes to studying the left HP equation. Rather than the inequality, if you make this equality here, that's a necessary condition for V to be isometric. It's not sufficient in the unbounded case. It is sufficient if F is bounded. But in the unbounded case, things can go a bit wrong. But the solution V being isometric is equivalent to your minimal QDS, the one turning up from doing this construction, being conservative. Okay. So quantum dynamical semigroups appear naturally when doing this thing, and they also have something to tell you about nice properties of your solution. Okay. So they are something that Franco has studied a lot. This conservativity here, or rather this, conservativity of T is a question that's of importance. So people have thought hard about it and said, given the G and the L, can I find some conditions that tell me it's conservative? That would then imply things about any solution of the QSDE. And there are necessary and sufficient conditions that exist in the literature, but they tend to be quite hard to apply. So there's been a whole raft of sufficient conditions. So things that can look quite scary, but the idea behind them is actually they're easier to apply than the necessary and sufficient conditions that people have developed. Almost all of these sufficient conditions start with this thing. Suppose you have a positive self-adjoint operator C. For any positive epsilon, I'm going to let C epsilon be this bounded regularization of C. Then there are results that run sometimes things like this. Start with the G and L that give me my quantum dynamical semigroup. So I'm not even doing solution to QSDs at this stage. That will give me a minimal QSDE T. If P is the semigroup generated by the G, suppose we have this bunch of conditions D, my nice subspace sits inside the domain of C, which in turn sits inside the domain of G. Assume it's a core for everything in sight. Some invariant, or rather, has to map certain vectors into nice places. Assume that happens. But what I really want you to look at is this inequality here. This is more or less my form generator, form the quantum dynamical semigroup, but applied to the unbounded operator C. Not a bounded operator now, but an unbounded operator. But it makes sense because of all the stuff up here that we have to check. For the quantum dynamical semigroup, we said this had to be less than or equal to 0, but now I've got a multiple of UC, U inner product CU. Okay. If that's the case, you can go away and you can prove that TT, the minimal dynamical semigroup applied to this bounded operator, is bounded above by this multiple of the unbounded operator C. Okay. Is that useful? Well, let's assume that the G and the L are things that give me a stochastic generator, so something to put in to trying to solve a QSDE. Assume there is a C that satisfies all these conditions just based on that first column, the G and L. If I know that, I'm going to get this inequality here. TT at C epsilon is the same thing as this inner product, or sorry, there should be norms, that should be the square of the norm here. Because when I write that out as an inner product, I will just be taking the vacuum conditional expectation. It hits my quantum dynamical semigroup, C epsilon, or C epsilon a half squared will give me back the C epsilon. That's bounded above by this guy here. This is true for all U's in D, every single T. The T is not going to vary for the moment. As I take the epsilon going to 0, right-hand side doesn't change, because there's no epsilon. Left-hand side, as a result, will be finite, and that tells me this guy here has to be in the domain of the square root of C tensored with the identity. So for certain nice U's and the vacuum vector, this maps into a nice place. Or at least I have some control. And control is what we're after here. So that works assuming I only want to stick the vacuum vector here. But I don't want to stick the vacuum vector here. I want to stick lots of different vectors here. I would like to be able to put in a dense subspace of vectors into U, T, and get them to be into the domains of these guys. If it's just the vacuum vector on the Fock space part, that's just a one-dimensional subspace. That's not a lot. Okay, so the trick for going from just the vacuum vector to more is this thing called the semigroup decomposition of cocycles. If U is a right cocycle, if I pick a pair of complex numbers, Z and W, I can always find an associated semigroup PZW defined this way. So again, it's like the vacuum conditional expectation, except what I've put in are not the vacuum vector this time, but my normalized exponentials, which are constant, given by the z and the w, and then put in the time, the indicator function up to time t. That works for any cocycle. I've said right cocycle, it equally works well for left cocycle. What I can tell you is that semigroup has to have a generator that extends this combination of the coefficients if v is the thing that solves the left HP equation and u is its time-reversed version. In particular, if z and w are zero, both zero, the vacuum conditional expectation, that lot all disappears. You're just left with g. So that's our original semigroup P. The other thing that's useful is this density or totality result. For any subspace of the complex numbers, I'm going to put 0 in it because it just makes my life easier. I'm going to assume it has at least 2 numbers in it. Blackboard bold, this ST here stands for step functions which take values in t. Okay, and they go to 0 after some finite time. That's easy to see. It's not a dense subset of L2, but it is a total subset. I can take linear combinations of these and get to near enough any vector in or function in L2. But the exponential vectors, where I take f from this nice set of test functions, that has dense linear span. Even if t is just 2 elements in it. So t here could just have 0 and 1 in it. So I'm taking functions that are 0 and 1 valued, step functions. The exponential vectors for those things are, when you take linear combinations, you get most of f. Moreover, my right cocycle, when I hit it with such a step function f and g on either side, splits up into a product of these semigroups, where these are just the values of the functions on each of the intervals it's constant on. There's some other factor out the end. So this splits it up into all of these different semigroups. The other part of the story for how to get to these other functions are, again, many thanks to KRP for introducing these this morning. I'm going to define the unitary Weyl operator WZT, so it depends on a choice of complex number Z. It doesn't do anything on this initial vector u. It acts totally on the exponential vector by adding in this multiple of the indicator function on 0t. There has to be a suitable scaling factor out the front to make it unitary. For any process x, xzt, I'm going to write for the process we get by hitting it either side by those Weyl operators. It was written on that blackboard over there this morning. So what else can I say? WZ, this process as t varies, that's both a left and a right cocycle. That's an example of one that satisfies both of those evolution equations. If you start with a right cocycle and you twist it this way with Weyl operators, you'll get a right cocycle again. You can change right to left. That works. If V is a solution of the left HP equation, the twisted version also solves the left HP equation. How do you sort that out? Well, one option is to apply the quantum eta formula to that product. There is actually a neater trick that involves not having to use the quantum eta formula, a bit easier to write down. This twisted version of it solves it for this generator Fz, where all I'm doing is I'm shuffling around components in this matrix, and I'm going to label them again with the z's in to say they're twisted. Okay. Just in time for the main result. Okay, so let's start off. How can I solve my right HP QSDE? Start off with this 2 by 2 matrix of operators. Suppose C is a positive self-adjoint operator. T is some subset of complex numbers, 0 in, at least 2 of them, so the conditions for this totality result from before. I want a dense subspace that's inside enough of my operators. It's inside, I'm saying here, the GZ, so the twisted version of G. So it's putting in bits of the K, the L, and the M. I'm going to assume that the GZs are all pre-generators of C0 semigroups, C0 contraction semigroups. In fact, D is going to be a core for everything in sight. I've got my form inequality. That will also still be true for the Fz automatically. This one I think I need at the moment, but I'm open to persuasion. Otherwise, I want the adjoint operator F star to do the same sort of thing on some dense subspace. And then, okay, ignore that line, but this bit here, this is the same form inequality I had for doing the control for a quantum dynamical semigroup, but what I've had to put in is I've had to put in the Z everywhere. Now, if my T here has only 2 elements in, one of these I said we were going to have anyway. I've got one other inequality of the same type to do. Those constants B to Z can depend on the Z. The choice of the constant there is largely irrelevant. It just has to exist. So suppose you've got all of that. Then UT maps this domain. This is a domain I can say that gets mapped into this domain of this unbounded operator. Domain of C1/2 is in the domain of GZ for all of these guys. So in particular, it's in the domain of each of these bits. It will follow that U maps into the domain of all of the G, the K, the L, and the M. Or rather, it maps this bit, the D tensor, with these particular exponential vectors. So that it looks a bit horrible. I did say it was unremittingly technical, so I don't get too stressed over, well, certainly anything, but not the details of this. For certain, we've got a bunch of examples, and all of these are relatively straightforward to check. I would like it that some of these things could perhaps be got from some of the other ones, and that's still kind of why it's still slightly work in progress. Basic idea of the proof, okay, well, given the F, I can solve my left thing. That will give me a cocycle, let U be the time reverse version of that. Get this control inequality for each choice of Z in my set of complex numbers. This will tell me this maps U tensor, this exponential vector that's constant on 0t into there. That's contained in the domain of all the components. Iterate. This is where the semigroup decomposition comes in. My U is when I hit it with exponential vectors of step functions, is a product of semigroups which will all act nicely. That will allow me to change this exponential vector that's constant on 0t into one that varies on 0t. Then you have to argue a bit about how U star, well, rather how U will map into, basically be able to differentiate on the right. So those are the basic ideas in the proof. I'm still on time. Good. I mean, a basic example we've got that does this, if I take little L2 on Z plus with standard orthonormal basis, I can take the usual creation annihilation operator on this L2 space. So I can do it here with this sort of quadratic version of the number operator. The appropriate choice for what the creation annihilation coefficients are given by A squared and A star squared here. The M in this case is 0. An appropriate choice for C. So what C here has to be a positive self-adjoint operator. It often helps in computations if it's invertible. It has to be, because I want these coefficients to, their domain should contain the domain of C, the square root of C. C, in a sense, has to be twice as unbounded as all those guys. A squared, A star squared are roughly the same as unbounded as the number operator, big N. That's what this N is standing for. So this will be roughly N squared. So this has got to be square of that again. So roughly N to the 4. So there's an example. I did say right at the beginning, I mean, again, keeping life straightforward, I've dealt with only one dimension of noise here. So the G, the K, the L, and the M are only supposed to be operators on H at this stage. One of the things that got mentioned in the felicitation yesterday was KBS's work with Anilesh Mahari on going to infinite dimensions of noise. So what happens if I want to expand this out into an infinite matrix of unbounded operators? Well, Franco and I have got a result from a long time ago on this sort of solving the right HPQSDE. There we could deal with K. What I've changed is I've put in a K here, which is the noise dimension space, as referred to by Martin this morning. In our previous work, that had to be finite, but it could be bigger than 1. Everything I've said so far assumed dimension of k was 1. But actually, our results now allow for separable infinite dimensional noise dimension space k. You'll have an infinite number of inequalities to prove. There is a cost here, but it's a bit easier to work through. The thing that's really improved, however, in our old version, we had to try and prove some form inequality of this form here. What's different to what I wrote down before is this is working this is an operator, a 2x2 block matrix, and here the C epsilons are all the regularized versions. That inequality is a pain to prove. And in fact, we never did an example where we proved it. What we have are sufficient conditions in the one-dimensional case that implied this. So that was in our JFA paper. So there's already a great benefit. This, rather than having to prove inequalities about a regularization of C, we can actually, what we're having to do is prove now is the inequality for C itself. We've also got things where we tried to make it work with our old method, and we sat there going, what do we take for C? It just doesn't work. And do we change the regularization? It still doesn't work. We think we can prove, in fact, that our old method can't work. But that's one of those sort of weird ones. How do you prove something doesn't work? This new method just seems to work better. So it's hopefully an improvement. Still a bit fun to check, but it does seem to be better. I'm on time, aren't I?
Yes.
Well, I've only got one more thing to say. You might want to wake him up. Cheers, Callian. This is available for sale in the US, apparently. But they wouldn't ship it to me, either in Ireland or in India. So.
Thank you, Steve. Very nice, clear lecture. Full of your typical modesty. I mean, the conditions you described as a bit horrible, but actually, you emphasize the fact that you only need to check it for 2. D can just be 0 and 1 in the one-dimensional case. Ameliorates it. And then on the other hand, you also said that when you go to multi-dimensions, you have an infinity of inequalities.
Yeah, but
If you cast them as matrix inequalities, does it not resolve itself into looking again?
yeah, you can write it as a big block matrix if you want and try and do it that way. But I think of our list of examples so far, I mean, to be honest, we've got one that's 2-dimensional and a whole bunch that are 1-dimensional. While it's theoretically true that our method applies in the informational case, I'm not sure we've come up with an example where we need that number of dimensions yet, but yeah.
Any other questions or comments?